Hello class, this is Mrs. Ayodeji with today's video on 11.5, the short run behavior of rational functions. As you're watching the video, feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring in the video. And at the conclusion of watching the video, submit your brief summary as well as your top question, deep thought-provoking question via the online quiz. Don't forget to write down important vocabulary formulas and equations and notes, because you can use your notes during the IPA. All right, let's begin. Today we're going to be continuing our discussion of rational functions, but looking at the short run behavior of rational functions. Now, as you recall, rational functions are the quotient of two polynomial functions, and so the short run behavior of rational functions can be determined from the short run behavior of the polynomial functions that make up the rational function. So let R be a rational function with polynomial p of x and q of x in the numerator and denominator respectively. The short run behaviors of p and q will tell us about the short run behaviors of R. Which short run behaviors? I'm glad you asked. The first ones we're going to look at are the zeros and the vertical asymptotes. So if I want to find the zeros of the rational function, or where it crosses the x-axis, all I need to do is find the zeros of the polynomial in the numerator. And once I find the zeros of the polynomial in the numerator, then that tells me where it crosses, the rational function crosses the x-axis. And that makes sense because the crossing of the x-axis only occurs when the rational function value is 0. And the rational function value will only be 0 when the numerator is 0. And you guys might be able to guess that the vertical asymptotes can be determined by the zeros of the denominator polynomial, which makes sense because whenever the denominator of a rational function is 0, that means you have a undefined value, which means you can have either a vertical asymptote or a whole. We'll get to that later. And in this case, for the most part, you have a vertical asymptote. Okay? So let's look at an example and apply what we've learned in our example. So here's our rational function. The polynomial in the numerator is a constant function, y equals 25, or p of x equals 25. The denominator polynomial is a third degree polynomial, and it's already factored for us to make life so much easier. So even though this is a third degree polynomial, it has exactly two vertical asymptotes, or two zeros, because it has two linear factors. So now that we know that information, we have enough information to figure out the zeros of our rational function, which there are none because this values will never ever be 0. So that's why we have no zeros. And the zeros of the denominator right here will give us the vertical asymptotes of the rational function. And those are x equals -2 and x equals 3. So now let's go ahead and graph what we know without using a graphing calculator. First thing we want to take advantage of is what's the y-intercept. You know how to evaluate the y-intercept. But just because I have the vertical asymptote and the y-intercept, it doesn't give me a full picture of what's going on. So we have to take a look at what's happening at these vertical asymptotes. So first let's take a look at what the graph is doing around the vertical asymptote of x equals 2. In order to do that, let's just try this out. Just plug in negative x for -2, -2 for x, and everything except the factor that would make this 0. And we end up with something that looks like 1 over x plus 2. Okay? Which means that during the x values that are close to -2, our rational function is going to look like the rational function of 1 over x plus 2, which means that basically it's the graph of 1 over x shifted over 2 units to the left. What does that look like around the asymptote? Well, it looks something like this. And the reason why I know it's this is because when x is negative, or approaches -2 from the left side, the values are getting bigger, bigger, bigger in a negative way, and the values are getting bigger, bigger, bigger in a positive way when x is approaching 2 from the right side. Okay? Doing the same thing, let's see what happens near x equals 3, the vertical asymptotes? Well, plugging in an x value that's close to 3, we're going to get something that looks like this, the rational function 5 over x minus 3 squared. And this is a little bit different because that function, as x approaches 3, is going to only have positive values because the denominator is squared, which means that it's going to hug the asymptote something like this. Okay, because the denominator is always positive, so as you get closer to 3 on the left and closer to 3 on the right, the output values are going to be positive. Okay? What about the long run behavior of r of x? Well, the long run behavior, because we're going to use the ratio of the leading terms of the numerator and the leading terms of the denominator, and that's going to be 25 over x to the third. That lets us know that the long run behavior as x approaches positive and negative infinity is going to be 0, because the denominator is growing much faster than the numerator, because the numerator is staying at 25 for very large x values and for very large negative x values. So let's put all of that together to get a closer idea about our graph. So here's our y-intercept around 1.4. Here we have, remember we had 1 over x plus 2, and that looks like this, but I have to go through the y-intercept. And then what's hugging the vertical asymptote over here, shift it over 3 units, and it looks something like this. So if I were to combine all of this with one graph, I'm going to use purple. This is my end behavior as it's going to, actually I should have done that, as it's going to negative infinity, the y values are approaching 0, and as it's going to positive infinity, the y values are approaching 0. But then over here in the middle, between these two vertical asymptotes, it's approaching 0 from this side. Gosh, I cannot draw. But then over here, it starts approaching infinity. Not 0. Why did I say 0? It's approaching infinity over from this side. So the graph looks like this. And you can plug the function into a graphing calculator to see how close our sketch looked. So in summary, we use the short-run behaviors of the numerator and denominator polynomial of a rational function to determine the short-run behaviors as well as the long-run behavior of the rational function. Now, some of you may ask some questions, and we're going to take an advantage of some of the questions you may ask. Number one, can a graph cross an asymptote? Well, for a vertical asymptote, never. But for a horizontal asymptote, sometimes, okay? And I'm going to show you a case where it can graph it sometimes. So here is an example of a function, a rational function, and based off the numerator polynomial and the denominator polynomial, we know that the zeros of this rational function are at -3 and 1, and that the vertical asymptote is at x equals 0, and that the long run behavior, because the leading terms, when you divide the leading terms by one another, they get to be equal to 1, and that means our long run behavior as x approaches positive infinity or negative infinity is 1, or approaches y equals 1. Now, as x is very, very big, then this function value will not cross 1, and when x is really, really big negative, the function values will never reach 1 as well. It's going to look something like this. Oops, wrong one. Okay. That's as approaching negative infinity and as approaching positive infinity. But somewhere in the middle, it actually does cross, and we're going to take a look at why that happens. In order for that to happen, it happens because at some point there is an x value where the numerator is going to be equal to the denominator to give us that y equals 1. And when will that happen? Well, that happens when this part is equal to 0. Okay? So, in other words, for our particular graph, we can determine when 2x minus 3 will equal 0, and that will be the point where a graph crosses the y-axis. And as you can see right here, oops, This is that point. Oops. Gosh, I can. Yeah, 1.51. Okay. So it is possible, but it's only possible if the leading term of the numerator and the leading term of the denominator are the exact same, coefficient and power. Okay. And if that's the case, we're looking for the values that make the numerator values equal to the denominator values. Okay. In this particular example. Another question that may come up is, how are rational functions related to power functions? Well, some rational functions are the result of a transformation of a power function, and not just any power function, but the power functions where the powers are negative integers. So if you remember our cost function from last video, we can transform this into a power function that's been translated by just dividing both sides, each term by q. And we end up with this. So really, this is a power function that's really moved up 2,000 units. Okay? The last thing we're going to do is we're going to find, not last thing, but almost last thing, we're going to find a formula for a rational function from its graph. Okay? So what we have here is we have a lovely rational function, and I know it's rational functions because it seems to have vertical asymptotes and things of that sort. And so let's dissect this graph based off the information we have. First of all, the y-intercept is 0.5, so that means our rational function is going to have a ratio of constant coefficients in the numerator and denominator to be 1/2. It looks like we have 1, 0 and -1, so that means x plus 1 is in the numerator of our rational function. And it seems to have odd multiplicity because it just passes through the x-axis instead of bouncing off. The vertical asymptote, there's only one, is that x equals -2, which means that x plus 2 is a linear factor in the denominator polynomial, and it must have even multiplicity. And the reason why I know it's even multiplicity is because, as you can see right here, the graphs are going the same direction as it approaches the vertical asymptote. So that must mean it must be squared or to the 4th or to the 6th power. So I can come up with a possible explanation right here. This is a possible formula, taking advantage of all those three things we talked about. The 0, the vertical asymptote as well. And we're going to use the fact that the y-intercept is 1/2. We're going to plug 0 into this function to figure out what k is. And as you can see, k is 2. Okay, so we're going to replace that, and now we have a possible answer. And if you were to graph this function, you would see it looks very much like this. This is a possible answer because we could have easily made this 4 instead of 2 because we needed to have an even power, but we didn't. Okay. Last possible thing. Is it possible for the numerator and the denominator to have the same zeros? Yes. And when that happens, how does it affect the graph? I'll give you a hint. It gives you a removable discontinuity or a hole, if you guys remember. So let's look at an example. Here we have a lovely rational function, but when we factor it, when we plug in 1, we see that we get 0 in the numerator and 0 in the denominator. Well, you would normally think that's undefined, but that's only undefined when 0 is in the denominator. There's a special type of undefined when they both are in zeros in the numerator and the denominator, and that's called an indeterminate. And you'll learn more about that in calculus because I'm not going to go into that right now. But it's indeterminate, which means we don't know exactly what the value is. And so let's look at why this is the case. Well, if I factor the numerator and I factor the denominator, I get a linear term of x minus 1 in both the numerator and the denominator. So if I were to divide those out, I end up with just h of x is equal to x plus 2 as long as x is not equal to 1. That means that this lovely rational function isn't going to have any vertical asymptote, isn't going to have anything in behavior that looks crazy what it's going to be is it's going to be basically a straight line with a hole in it, because even though x plus 2 is a straight line, h of x can include every number in its domain except 1, so we have a hole right here. So you have to watch out for the case where the numerator and the denominator have the same linear factor, because that doesn't mean you're going to have a vertical asymptote. It means you're going to have a removable discontinuity, which is a hole.